So our topic for today is going to be a new topic for everyone. It is implicit differentiation. So far, all of our equations that we've done derivatives for have been something called explicit equations. And an explicit equation is one that you can rearrange to get y by itself, y equals. And then you can use your derivative rules, which is our chain rule, product rule, power rule, quotient rule, to find the derivative. An implicit equation is an equation that is a relationship between two variables, but may not be easy to get y by itself. So for example, this is an equation of a circle. X squared plus y squared equals 16 is an explicit equation because it can't be written as just one equation by itself. If you tried to get y by itself, can you see that you could first subtract x squared? But then if you wanted to get y by itself, you'd have to square root both sides. Well, what do you know about square rooting both sides? You have to add that plus or minus. So what that means is you actually get two equations for y. It could equal the positive 16 minus x squared, or it could equal the negative 16 minus x squared. And this is why this is not a function. It is actually something else. And if you were to graph this, this would make a circle with a center at 0 and a radius of 4. Now, when you have these kind of equations, you can do implicit differentiation. You can still find the derivative of them, even though you have two different variables. So the way that it works is you imagine that you could get y by itself and that y is a function of x. And to find dy dx, you take the derivative with respect to x of everything that you have. So if I take the derivative with respect to x of the left side of my equation, and I take the derivative with respect to x of the right side of my equation, this is what will happen. What's the derivative with respect to x of x squared? Well, that's easy, because I know how to do that. That's just going to be 2x. But this is where things get tricky, because we need to take the derivative with respect to x of y squared. And there's no x's there. But we're told, or we are thinking, that there is some equation. If we rearrange this, there is some equation that has x's in it that we could say y is equal to that. And now we want to find the derivative of this whole thing squared, because we're trying to find the derivative of y squared. Well, how would we do that? Even though, you know, we have, I'm going to put that in there just as a thought, because we sort of simplified that on the other page to have it look like that. And I'm going to think, if you had this and you wanted to find the derivative, does it make sense that you could do the chain rule and do the outside function first, which is bring the 2 in front and subtract 1 from the exponent, and then do the derivative of the inside? That's what we're going to do at this point with our y. If we did a chain rule, the outside function would be the squared. What would we do? We'd bring the 2 out in front, subtract 1 from the exponent, so you get 2y to the 1. And then after we do that, we'd have to multiply by the derivative of the inside function. Now, the inside function is y. And if we could get y by itself, like we did here, what would the derivative be? Well, the derivative would be the derivative. The derivative of y is dy dx. And the derivative of 16 is 0. If we wanted to find out what the derivative was by itself, could I get dy dx by itself at this time? Well, I just have to subtract the 2x over to the other side and divide by 2y, and that would be my derivative, even though I don't know what the equation of y is in terms of x. So what I'm going to do is I'm going to do this same thing with a simpler equation. Let's say you don't have to write this down. Let's say that y is equal to trying to think of one that would be easy enough to work with. Maybe I'll just work with the one that we had, the x squared plus y squared equals 16. Because if you got y by itself, which we had in this one or this one, one is positive, one is negative. Could we find the derivative? Well, how would I find the derivative of this one on the left? Well, first of all, I would change the square root to a half. And can you see that you could do a chain rule? We've got a function inside of another function. So my derivative here would be 16 minus x squared to the negative a half multiplied by the derivative of the inside, which would be negative 2x. If I rearrange this, that negative the half could be 16 minus x squared on the bottom. The 1/2 in front could be a 2 up there, and I have a negative 2x on the top. That's if I did the derivative directly, having solved for y by itself. This is what I get as my derivative. Using implicit differentiation, what did I get as my derivative? I got negative 2x over 2y. So using implicit differentiation, I got negative 2x over 2y. Can you see that those are the same? Just in one case, I got y by itself and did the derivative. In the other case, I said, I'm just going to pretend that I could get y by itself, and then I'm going to find the derivative based on that without actually ever finding out what y is by itself. Now, this first equation, I was able to get y by itself, and so I could show that these two are the same idea, that they come out to the same thing. There are some equations that we're going to do that there is no way, there is no algebraic way that you can get y by itself. It's impossible. But we'll still be able to find the derivative at that point. So now going back, now that we've looked at this original equation and said, if I got y by itself, and here I chose the positive one, and I found the derivative, it's equal to negative 2x over 2y. And just for fun, let's see what happens if we had done the negative version. Does it still work out? So with the negative version, we would have y equals negative 16 minus x squared to the half. The derivative here would be bring the half in front. 16 minus x squared negative a half multiplied by negative 2x. I still have the 16 minus x squared on the bottom. I still have a 2 on the bottom. And on the top, I have a negative times a negative, which is a positive 2x. Does this match up? Do I have negative 2x over 2y? Well, here I have 2x. Here I have 2. Is this y? No, it's missing the negative. So there would be a negative there in order to match it up. And sure enough, if you move that negative to the top, this is exactly the same. So even though we'd have two different functions we'd have to do the derivative of, because solving for y gave us two different equations, we get the same pattern with both of those. That the derivative of this one will be negative 2x over 2 times whatever y is. Now what's interesting is if you graphed this circle and you wanted to find the slope of the tangent line at a certain point. So for example, when x is 1, y would be the square root of 3, because that would make x squared plus y squared equal to 4. What was it, 16? Is it x squared plus y squared equals 16? 15. There we go. That would still be a point on this circle. If I wanted to find the slope of this tangent line, the slope of this tangent line will be negative 2 times 1 over 2 times the square root of 15. And now when I want to find that slope, I have to plug in both an x coordinate and a y coordinate. Everything we've had up till now only had to plug in the x coordinate to find the slope. But this equation, these implicit equations, you'd have to plug in both the x and the y coordinate because our derivative has both variables in it. So the big idea is you take your derivative of everything with x exactly the same as you have in the past. So when I take the derivative of the whole equation, the derivative of x squared is just 2x. The derivative of 16 is just 0. That part stays the same. But you take the derivative of anything that has a y like a chain rule. In other words, you do the derivative like normal. So what's the derivative of y squared? It's 2y. But any time that you have a y in your equation, you then have to multiply by dy dx because that would be the derivative of the inside function, the chain rule happening. So let's look at another example rather than just doing this example over and over again. Here is a great example of how impossible it would be to get y by itself. If you'd like to spend the next 7 days trying, you can, but you won't be able to get y by itself without having a y on the other side. Sure, I could get one y by itself, but I'd still have y's on the other side. But how would I get y by itself so the other side just had x's? You know, last one we had 2 possible equations. This one with y to 7, maybe there'd be 7 different possible equations you'd have to come up with. And none of them would be fun or even possible. So in order to find our derivative, we're going to have to use implicit differentiation. And the way that that works is we take the derivative with respect to x of everything. And we say to ourselves, we know that y is a function of x, even though we don't know what it looks like. Despite that, we can still find the derivative. So how does it look? Well, I'm going to do the derivative of this whole thing. So as far as showing my work, I can say I'm going to take the derivative of this entire equation. And so I'm going to take the derivative of each thing separately. This one is going to be easy because it just involves x's. What's the derivative of 3x to the 4? It's 12x squared. What's the derivative of negative x cubed times y? Well, x cubed is one function, y is another function, and I'm going to have to do the derivative of both of those. They're multiplied together, so that is, yes, thank you for noticing. This is just a 3 in the process. I'm going to have to use the product rule for that negative x cubed times y. How do I do the product rule of that? I'm going to make that 3 better. So I've got 12x cubed. Product rule says keep 1 the same. So let's say I keep my x cubed the same. The derivative of y is the derivative. And I like to use Leibniz notation here because then my dy dx really sticks out. Plus, keep the other one the same, times by the derivative of the first one, 3x squared. Equals, the derivative of 15 is 0. The derivative of y squared, again, it's a chain rule. If you do the squared first, the 2 would come out in front. Yeah, it's a 7. Is that the other thing everybody was looking at? There we go. So bring the 7 out in front. Subtract 1 from the exponent. And then the derivative of the inside is dy dx. So sometimes what students sort of see as their shortcut is whenever I'm doing a derivative with a y, I do the derivative like I normally would. Like what's the derivative of something to the 7? Bring the 7 in front, subtract 1 from the exponent. And then if it has a y, I always multiply by dy dx afterwards. And that is sort of a shortcut that some people use. The reason that you're doing that is because this function y, we don't know how to do it, but it is a function of x. There's some equation that we don't even know what it looks like. It's out there. And if we did the derivative, we would get dy dx equals something, which we also don't know what it looks like. So what we do is when we don't know what it looks like, we just leave the y there. And we just leave the derivative there, even though we don't know what they look like. With just x, we have no idea. But we know that it's there. Now that we've done our implicit differentiation, we've done a derivative of each thing separately. Now we have to use our algebraic skills to try and get this dy dx, which is here and also here, by itself. And since they're just single things where they are, all you're going to have to do is like you did for solving for x. You're going to bring all the terms with the dy dx to one side of your equation. So if I were to do that and bring them all to the left side, do you see that I'd have a negative x cubed dy dx? And if I brought this one over, I'd have a plus 7y to the 6 dy dx. And if I moved everything that didn't have a dy dx to the other side of the equation, my 12x cubed would be a negative 12x cubed on this side. And this negative y times 3x squared will be a plus, I'm just going to multiply it out, 3x squared times y on that side. So I've moved both the terms that had the dy dx to one side of my equation. And now that I've done that, if I want to get that dy dx by itself, factor it out. Factor out the dy dx. Leaving you with a negative x cubed plus 7y to the 6 And now if you divide both sides, you will get your derivative by itself. So again, we can't write our derivative just in terms of x. Our derivative has x coordinates and y coordinates. And if you plugged in an x coordinate and a y coordinate, you could find out the slope of the tangent of that function at that time. So what we're going to do is we're going to take the derivative with respect to x of this whole thing. I'm going to change the cube root of y to y to the 1/3. So now the derivative with respect to x of x squared is just 2x. Whenever you have a y, what we're going to do is we're going to just do the derivative like normal. So if I had a y to the 1/3, how do I do that derivative? The 1/3 would come out in front. I would subtract 1 from the exponent, and I would get 1/3 y to the negative 2/3. But every time you have a y in your function, after that, you're going to apply the chain rule and say, my inside function was y. What's the derivative of y? The derivative of y. dy dx equals. In the next term, you have two functions multiplied together, so you're going to have your product rule. Your product rule says keep one the same. So if I keep the first one the same, multiply by the derivative of the second one, well, that would be 3y squared, but every time you do a derivative with y, you multiply because of the chain rule by dy dx, plus, now keep the second one the same, multiply by the derivative of the first one. Now when we do the derivative of this first one, there's no y, so you don't multiply by dy dx at the end. And then we have to do the derivative of 8. You don't have to write plus 0, but if you want to just make a mental note that you did the derivative of that 8 as well, this is what you would get. Where do we have dy dx? We have one here. We have one there. So to solve and find dy dx, we need to get that by itself. So every term that has that dy dx we'll bring to the left-hand side of our equation. And every other term will move to the right-hand side of the equation. Now you have a dy dx in both of those. You could factor that out. And if you want to skip right to this step, so I'm going to multiply those things out. On the other side, do you see that I'm going to have 12x squared y cubed minus 2x on the top? And when I factor out the dy dx, my next step would be to divide whatever was in the brackets. So can you see in the first term, you would have a 1/3 y to the negative 2/3. And in your second term, you're going to have, well, if I multiply those together, I'm going to get 9x to the 4 y squared. And that gets you dy dx by itself. If you like to do that extra step with the factoring, would be to factor out your dy dx, leaving you with 1/3 y to the negative 2/3 minus 9x to the 4 y squared equals 12x squared y cubed minus 2x. And then you'd have to divide by this to get your final answer. So we use implicit differentiation when we have a variable of y that often has a y squared or a y cubed, and it's not easy to get that variable by itself. Then you'll get an equation for your derivative that is in terms of both x's and y's. So at the beginning, I was thinking about an example. I think I have a good one now of where we could use implicit differentiation or we could use regular differentiation. Something that you could solve for y by itself if you wanted to. So let's say I had y cubed equals x squared plus 7x. And right here on this side, I'm going to find the derivative with implicit differentiation, and on this side, I'm going to find it with regular differentiation. So implicit differentiation says take the derivative of the whole function. So when I do the derivative of the left side of my equation, I'm going to get 3y squared times dy dx. And on the right side, I'm going to get 2x plus 7. So my derivative by itself will be 2x plus 7 divided by 3y squared. Using regular differentiation, you would have to get y by itself. The way that you would get y by itself is you would have to cube root both sides. And if I cube root both sides, that would be the same as writing this as the power of 1/3. Now, if I wanted to find my derivative, dy dx, I'd have to do my chain rule. My 1/3 would come out in front. I'd have x squared plus 7x to the negative 2/3 multiplied by 2x plus 7. If I rewrote this on the right-hand side, I'd have dy dx equals 2x plus 7 on the top of my equation over 3 times x squared plus 7x to the positive 2/3. So in one way, I found my derivative using implicit differentiation. In the other way, I solved for y and used regular differentiation. Question for you is, can you see that these are the same? And the way that we see that they're the same is either we take what y is equal to and substitute it in for y. And if I would take that, either that form, it's probably even easier to use this form. Can you see if you plug that in for y and then square it, you would get that to the 2/3. Or the other way is to look at rewriting this side. I'm going to change this x squared plus 7x. I'm going to take that 2/3 and go 1/3 squared. Because 2/3 is like doing to the power 1/3 and then squaring afterwards. And this part here is just y, and it matches up with this. Now, so both work. What's nice about implicit differentiation is you don't have to first get y by itself in order to do it. In fact, you can do it even if you can't get y by itself, which is where it's really powerful. And by not having to get y by itself, often finding the derivative is easier and more straightforward. You just get an equation in terms of x and y instead of just an equation in terms of x. So that's implicit differentiation. Now it's your turn to practice some. So page or section 2.7 on page 107. We'll take some time to try some of those, and I will go back and do the first questions again for those of you that just got here.